Alright, my name is Camilla Dartnell, and this is the physics calculated for the world's largest rope swing. So the first thing that we needed to do is draw a picture, and on this picture I've labeled all of the heights that were given to us in the world's largest rope swing behind the scenes. And I've calculated my heights into meters, and we're going to use these later for the heights within this physics. So the first thing we want to calculate is the speed at the bottom of when the person is at the very bottom. So we're going to use the energy principle, and we can assume that delta E equals work, and at this point then it's a closed system, so that equals 0. There's no work being done. So E final equals E initial. We can plug our kinetic plus potential final equals kinetic plus potential initial. We can assume that the kinetic initial equals 0, and that's because initially then you're stopped, you're not going anywhere. Okay, and then we can cancel out all of our masses because we have a mass in each one. And so we get a final velocity at the bottom to be 29.95 meters per second. The second thing we want to calculate is the tension at the bottom. So when our velocity is 29.95, what is our tension? One thing that I'm going to use my mass, which is 50.3 kilograms within this calculation. So we know that the force total equals the force of tension minus force of gravity at this point at the bottom. And then we can plug in that we know the mass times velocity squared over r, which is the length of our rope, equals ft minus mg. And then we can just plug and chug all of our already known numbers, and we finally get a 1480 or 1,480.3 newtons is the force of tension at the bottom of the spring of the swing if I was riding it. So then we're going to do this exact same thing, except for we want to find the speed and the tension at 30 degrees now. So again, we're going to use the energy principle. Again, we're going to initially cancel out our kinetic energy because it's going to be U, and use all of those same exact equations. And then the only thing that we're going to change is I'm going to include like a cosine 180 minus 30 to account for the 30-degree angle. So using just plugging and chugging, we get our final velocity at this point, 30 degrees, to be 27.58 meters per second. And then the tension at this 30 degrees to be 1,264.189, again, assuming my weight. Okay, and then the next thing I want to find is the stretch at the bottom and the stretch at 30 degrees. So I'm going to use a spring constant of 29,000 newtons per meter, and then we can use the equation, the tension force equals this spring constant times the distance change, so S, and just rearrange the equation, plug and chug, and we get 0.0510 meters at the bottom is going to be the distance change, and then the stretch at 30 degrees is going to be 0.04359, which, as you can see, is a little bit less, and which is good. That's what we want, because the tension force isn't as great at that point. All right, and then I'm going to bring you over here to my code. So this code is mainly based off of our spring lab code. And I do all the same calculations. I'm going to run the code, and it shows you what this swing would look like. A pendulum. And it's going to stop at, this is at the 30 degrees, and then it prints the velocity at 30 degrees, which is 27.57, which is almost exactly what I got through the calculations. And so through that, then we know that my calculations were correct, and that is the physics behind the world's largest rope swing. Thank you.